Hi everyone, my name is Juan Pablo Solano. Welcome to this new video of YouTube. So here we will speak a bit more about segment routing traffic engineering, and actually the topic I have for you today is on demand. So on demand is a variant that we can configure in segment routing traffic engineering for calculated and created our policies, right? So as you might know, segment routing traffic engineering has different flavors, right? So first is the manual flavor, that you configure the policies manually. Later it comes with dynamic policy creation, and this actually is the feature that we will see now, that is on demand. And the third one is, the third and not least, is actually PCE, right? So the PCE is the controller, so it's like the brain holder for all the policies. And this open basically the automation part within segment routing traffic engineering. So what we will focus now and today is about on demand, right? So for that, I will probably speak about how traffic engineering works in other videos, but just for you to understand how traffic engineering works, SR is basically the replacement or the evolution, it's better to say, than for LDP. Both of them are labeling protocols. So LDP is a labeling protocol, SR also is labeling protocol, and both of them are actually or fits within the MPLS concept, right? So how SR works, normally in our environment, for example, let's take the picture here. We normally have the PE to the route reflector, they have a multi-protocol BGP session, right? So this can be a BPN-V4, BPN-V6, depending of the service, it can be EVPN as well. So here, the route reflectors have a BPN-V4 session towards the PEs, in this case P1 and P2 here, this is wrong. And normally a layer 3 VPN, well, this is known as a layer 3 VPN, is equal to BPN-V4. Normally in a layer 3 VPN, we have different other aspects, right? We have, for example, in the PEs, we have a BRF here, BRF, and within this BRF, we have also the route targets, route distinguishers, that those are known as extended community, right? So also we have a PE to C protocol that we run between the PE and CE. So it can be BGP, it can be OSPF, it can be EdgeRP, it can be any routing protocol you like, even a static route as well. So normally in a layer 3 PN service, the CE advertised to us the prefixes to the PE. In my case, this is the scenario that I have. So C2 advertised the 200/32 prefix to the P2. P2 advertise to the route reflector, it redistribute the prefix to the route reflector. Route reflector reflect the route towards the other PE, and P1 basically import that route into the BRF. It imports using the route targets, right? We'll explain probably a bit later what is route target in another video, but the P1 receive the prefix and import into the BRF using route target. And the route reflectors obviously have both PEs as a route reflector client, right? So the P1 import the prefix and send it back to the C1. Here also we have a PE to C protocol, right? So it can be BGP, it can be SPF, whatever protocol we want, it can be working here. So the P1 advertise a prefix towards the C1, let's say the 200, and that's how we have actually the bidirectional communication. C1 also advertise same prefix, it goes to route reflector, goes to P2, P2 import and send it back to C2, right? That's how it works. Now, on top of that, if we want to enable, let's say that we have our core segment routing here, and we want to enable segment routing traffic engineering, let's imagine that the path for this traffic flow of the layer 3 PN goes here, and we want the path to go here, then we create a policy, segment routing traffic engineering policy, and there is where our topic is for today, right? So we have manual policies, we have dynamic policies, and we have also the PCE, the automation, open automation for segment routing. For manual policy, if you want to create a manual policy, you first need to define the name of the policy. Later, you need to define the color, what color you want for the prefix. So what this color means, this color is an extended attribute in BGP. So it's meant for segment routing. So basically, I'll explain you in short things. When the P2, for example, receive the prefix from the C2, the 200 prefix, and it advertised to the route reflector, there is a chance here that in the moment that we advertise to the route reflector, we can assign a color, right? We can assign a color. This color can be, for example, blue, color blue. This is inserted into the BGP updates. And also whatever the attributes are for the prefix is where this color resides, right? So this color is attached to the prefix, to the updates. It goes to the route reflector reflects the routes towards the PE, and PE1 receives the prefix 200 with the extended attribute that is called color blue, right? So this color is an extended attribute, right? It's the same extended attribute as route target, route distinguisher, but it's for different purpose, and that purpose is segment routing. So at the moment that we define the manual policies, we need to define the color. Why? Because we need to match the color that we want to route the traffic through the network with the color that we are receiving from the route reflector for the specific prefixes. So here we can say color blue in the manual policy. Then I say to which endpoint I want to reach. So basically this is the next hop of the prefix. In this case, for example, P1 would like to have this policy of traffic engineering towards the loopback of P2, that is 2222, right? So I need to define here the loopback of P2. And then later I define how I want to calculate the path for that policy. I want to calculate based on low latency. I want to calculate based on low IGP metric, low T metric, right? So if we want to calculate based on low latency, obviously we need to have a protocol that can measure the latency in all the network. And that protocol is perform measurements. I will repeat again, is performance measurements, right? So this protocol is responsible for calculating the delay in both directions and advertise this towards ISIS. So then all the routers are aware that what is the latency for every link, and then they can choose the lowest one towards that particular destination for that color. Okay, that's how manual policy works. You know, there are many layers that we need to configure in manual policy. It's very useful because we can define explicit paths. So we can say, I don't want to rely on your brain in the network to calculate the lower latency, but instead I want to define the path to go to here, right? So in the case of ODN, that is a dynamic way, we don't care about the name. The name is auto-generated, right? Based on the BGP, right? Then we care about the color, obviously. We need to define, hey, for this type of prefixes that has the color blue, I will define my policy that will have a constraints, or I would like to calculate based on the low latency, based on the low metric, and so. As you can see here, there is no any endpoint that I need to define as in manual policy. So in manual policy, we have to define the name, the color, the endpoint, and the constraint. In the ODN, we don't define the name, and we don't define also the endpoint. The endpoint is received, or the router relies to who he needs to send or create the policy based on the BGP updates that he received. So he received the BGP updates, he checked the color, he checked the prefix, and also he checked the endpoint. And that's how the router automatically creates the tunnel to that particular endpoint. So this saves a lot of configuration actually, and the configuration is much more simple, much more easy to manage, and obviously it's not that specific as we can do with manual policy, so always there is a trade-off, right? So you have ODN for specific services, probably it's too easy to configure, it's too easy to understand, but also you lose in some way the precise or the tune a bit the policy to specifically to which destination you want, to which you don't want. So it's a trade-off that in some networks can be advantage, in some of them probably manual policy is best. But that's how ODN work. It's a dynamic way for configuring policies in traffic engineering. So, and the color, again, color is received or is getting from the updates in BGP. That's how the color is mapped into the policy, either manually or ODN that we define. Saying that, we have this lab here. We have ISIS. We have segment routing enabled. There's two commands that we need to use for enabling segment routing. First is, well, metric. You must not forget about metric style wide. We need this command for segment routing to work. We need also the segment routing MPLS SR prefer, because by default LDP will be preferred if you have LDP on the underneath. But if you wanted to replace with segment routing, you need to basically you need to enable this command for prefer segment routing over LDP. And the last one is the distribute link state. Distribute link state. So this is not specifically for segment routing, but this is specifically for traffic engineering. We want the device normally in segment routing advertise their links and attribute of the links towards the domain. So for that, we need to we need to tell the device that they need to advertise those metrics. They need to advertise what is the lattice in this link, what is a metric IGP here, what is a metric of TE here. So we need to advertise for obviously the PE to be able to create a policy towards the other PEs. They need to be aware of everything. That's why we need distribute link state level 2. Sorry for my grammar, but I hope you understand. And the last but not least, that is it causing some problems whenever we are testing in a lab or things like that, is that all the links for segment routing traffic engineering must be in point-to-point, right? This is quite common in Service Provider Network because we don't want to have a broadcast link defined. We don't want to work for the D selection or for the DR, BDR in case of SBF. We want to interface to bring it up faster. So that's why it's best practice to configure point-to-point, and actually without these links defined as a point-to-point in ISIS, segment routing would not work, okay? So saying that, we have in this domain, I think that I already configured ISIS, is already done. I have segment routing also defined. This is prefix seed 16001. This is prefix seed 16002, and the others I didn't define. I defined the links as a point-to-point. I also created distribute links, distribute link state for advertiser prefix. So what all we need to do is to configure ODN in this router for the color 100. Here in this PE, I have already configured coloring, meaning that I receive prefix on the PE1. When I advertise this prefix to the BGP, I mark this color as a color 100. Then on the PE1, I need to define the ODN policy for creating the policy on the color 100. We'll see how it works. So let's first go to the device, the PE1. I will show you what configuration is needed for ISIS. So you need, for ISIS and segment routing to work, you need this command, metric salwat, distribute link state. Sometimes I think in some versions you might need MPLS traffic engineering as well. That is the oldest way to do it for LDP. In recent, probably you don't need this, but I just added because my version is not updated. Then this command, segment routing MPLSs are preferred. That's also required. As you can see, I also defined a prefix seed attribute for the label, and the links as point-to-point. I did this in all the devices. In all the links are defined as a point-to-point. And this configuration also should be applied in all the devices, in the provider router as well and the PE as well. So we have that information already. How we know that we are receiving the information through ISIS? Well, we can configure show ISIS segment routing. Actually, show segment routing traffic engineering. Actually, here we can do IPv4 topology. And here you can see this is the same equivalent as show MPLS traffic engineering topology, but this is for segment routing. Here we see all the database that are being propagated. So this is node 1, node 2, the router ID, node 3, the router ID, and node 4, also the router ID. So we have all the information around all the network. Now, let me test ping between P1 and P2. So actually, this is pinging the loopback. I will ping the loopback towards the P2. This is not P1, it's P2. So let's try the link, the ping. It works. Now let's ping by SR MPLS 222/32 source loopback 0. I think that here I need to define manually the source. Okay, it works, meaning that our path is labeled. Now in the Cs here, I forgot to tell you, I am advertising here the prefix 100/100/32 and here 200/32, and this is a layer 3 VPN service. So I have VPN before here, VPN before here. This is VPN before, VPN before. I did just a simple for being very explanatory. So here I'm running BGP, and here also BGP, here IS 300, here IS 200, and here IS 100, that is the core. Okay, so let me do a pin between the CEs loopbacks. So for example, here I will go through ping the loopback of the other CE that is actually 200, 200, 200, 200, source loopback 0. It works. Let me trace route, this prefix, source loopback 0, numeric. Well, I think that here I need to, even I don't need this one here. Perfect. So now it's labeled, right? So now let me just create the on-demand policy in the P1, right? So how you create that? You do to segment routing traffic engineering on-demand color 100 is the color that I'm supposed to receive from P2. Here I say dynamic calculate the path using the metric of the IGP, type IGP. So what I did was, in the P1 I told him, please calculate on-demand policy, dynamic policy for all the prefixes that have the color 100 and calculate the path in the network with the lowest IGP metric. So if I commit this here, then this policy is applied. Now I need to receive the color for the prefix. So what I did was I went to P2 and I created the community for the extended community with the color 100 for all the prefix that P2 is sending to the route reflector. So I created a policy here that holds and mark all the prefix that P2 is forwarding to the route reflector, mark this prefix with the color 100. So I will show you what I did. So here I created extended community set opaque blue. Here you see the color 100. Then what I did was to apply and create a route policy, right? Route policy that basically set this color to the route policy, and I apply this policy to the route reflector. So as you can see, this is the policy that I applied to the route reflector in the outcome direction. So I'm marking all the prefixes that I am advertising to the route reflector with the color 100, and the P1 should see those prefixes. So for example, if I take a look in P1 to the loopback of the C2, this loopback here, P1 should receive this prefix and also should receive as an extended community with the color 100. This perfectly match our color. So meaning that on-demand policy should be up. Let's take a look. Traffic engineering, on-demand, and actually here you can just put policy. And if we put name, you can see that the name is auto-generated, right? Directly. So here we see that the policy is up, and the path it goes through the prefix seed of the loopback 0 of router P2. The metric you see also is 110. That's the accumulated metric, and the candidate path is a preference. It's calculated in dynamic way, and the metric type that I use is IGP. So this means that my policy is up. Now, how I know that when C1 wants to send traffic to the loopback 0 of C2, let me just clean this a bit. How I know when C2 send traffic to the loopback of C1 send traffic to the loopback of C2, how I know that P1 indeed is really using that policy? Well, there is a way that we can check the BRF and CEF actually in the BRF for that particular, obviously, BRF that is configured there for that particular prefix that he wants to reach. In this case, he wants to reach 200/32. So I can check which shows CEF BRF, the loopback of C2. I can see, and I will show you, my VPN or BRF name is blue VPN, and here I put 200, 200, 200, 200 /32. Here I can see that the next hop is basically the policy name of that particular policy that was just created, right? So the name is actually attached into the policy. So once I check again the policy, when we took a look here, then we see that the policy is up and running. Actually, here also you can see a local label, right? This is called binding seed, binding segment ID. This is a local label originated by the router automatically or can be manually defined. And this also represents and helps the policy to be pointed for each now this prefix, basically attach the policy of segment routing traffic engineering into this prefix in the forwarding information base. So this binding seat is very important for that, for basically help to push the policy in stress. But obviously, if you want to be more precise, then you need to create more tuned SRT policies. That's what's all for today. And yeah, enjoy the video. Have a nice day. Bye.